Okay, today we are going to start with session 10. We are not going to be doing any hands-on exercises on that because we're a little bit late behind the schedule, but I'll just quickly talk about the small watershed boundary condition feature and point out some of the input parameters in these files, and then look at the results in terms of the small watershed budget files. And then I'll move into showing you some of our tools that we have developed over the years. Most of them are built into GIS. Maybe you'll find them useful. Okay, so basically these small watersheds act as kind of a dynamic boundary conditions for your model area, both for surface and subsurface flow in your model area. So let's say that this red line here is your model boundary. You have a Mr. Potato Head looking boundary here, and you're simulating these streams, and you can have these rim watersheds that are supplying water, both surface water and subsurface water, into your model area. So we have a fairly simplified way of simulating those dynamic flows into your model area. In Central Valley, for instance, these are the rim watersheds in the foothills in the east and the coastal mountains on the west. We in situ simulate about 210 of them. Okay, so in terms of the subsurface flow contribution from these small watersheds to your groundwater basin in your model, again, it's a very simplified way of looking at it. We basically keep track of a storage in the small watershed, groundwater, and then we multiply that storage with a coefficient, what we call recession coefficient. So we basically take the storage and try to relate that storage to a flow. That's all we do. So this term is the groundwater contribution from your small watershed to your model domain. For the surface flow contribution, what we do is we basically ask you to specify a threshold for the groundwater storage. Anytime the groundwater storage goes beyond that threshold, we say, okay, let's look at the difference between your actual groundwater storage in the small watershed and that threshold, and we multiply that difference with another recession coefficient, and we say, okay, this now is the surface flow. It's almost like the groundwater return flow, onto the surface in the small watershed, which then becomes a surface boundary inflow to your model area. And then we put these two terms into the mass balance equation for the small watershed. So we basically start with the initial groundwater storage in the small watershed. We calculate the percolation. We actually simulate the root zone, just like we do in the real model, the root zone component. We simulate the percolation, which is the recharge to the small watershed, and then we subtract any subsurface outflow and the surface outflow from the small watershed to calculate the storage at the end of the time step. As I said, percolation is calculated exactly the same way we calculate in the IDC using either Campbell's or Van Genuchten-Moellem equation. Probably you will remember this from the IDC component, the root zone component. This is the mass balance equation that we use for the root zone. We calculate the rainfall runoff, percolation, ET from the small watershed. So you basically, if you look at the input parameters for the small watersheds for the root zone part, you have to specify the same parameters: fill capacity, total porosity, wilting point, so on and so forth, and the ET and the precipitation. So let's say that you have your model boundary here, and you have identified your nodes. This is your mesh here. And these are the streams that you're actually modeling. And here is your small watershed that you decided to simulate as a dynamic boundary condition. But let's say that in real world, in real life, there's kind of a small creek here that is going from your small watershed right at the boundary down to a stream channel that you're actually simulating. So IWFM gives you the option to actually simulate this as a stream with the methods that we have seen yesterday. Or you can say, well, this is just not that important to me. I don't want to deal with this. You can just say, okay, any water that is coming out of the small watershed as surface flow will travel through these groundwater nodes, and as it is going through these groundwater nodes, it's going to lose up to a certain amount of water as percolation down to the groundwater. So we are not really routing anything. As the water is moving from here to here, we are basically subtracting some flow from this node, putting into the groundwater right there. We are subtracting another flow from this node, putting into the groundwater node. You know, it's just another way of, very simple way of doing, trying to move the water from the boundary down into the stream. Okay, so the second half of this presentation is about simulating the groundwater in multiple aquifer layers. Up until now, all these 9 sessions, we've been always looking at a single aquifer layer. This is the presentation, just repeating from the very first session, and we are really going to concentrate on these 2 components here. If you're looking at the aquifer layer, you can have flows, vertical flows into it from the upper layer and the layer below. Just to remind you again, you can either have aquifer layers in your model that are separated by actual hydrogeologic formations like clay layers. If that's the case, this is the flow term that we use, leakage of this clay layer times the head difference between the 2 aquifer layers, and the leakage is essentially given with this form, hydraulic conductivity, vertical hydraulic conductivity divided by the thickness of the clay layer. If your aquifer layers are mostly numerical layers, right, you don't necessarily have a geologic formation, hydrogeologic formation that is dividing your 2 aquifer layers. In that case, this leakage term is represented as the harmonic mean of the individual conductance terms of the 2 aquifers. And then when you put that into the conservation equation, they come out again like this. These i's, I sub u, I sub d are 0 and 1 again, which tells the model if you're looking at a top layer or bottom layer, so that if you're looking at the top layer, this term just disappears because there's no flow, there's no more layer from the top. If you're looking at the bottom layer, bottommost layer, you don't have any flow at the very bottom because you're already at the very bottom.